السلام عليكم ورحمة الله. اليوم إن شاء الله نتحدث عن linear algebra. بالدرجة الأولى we'll discuss an introduction to linear algebra in its abstract form في شكلها المجرد. The main building block in linear algebra is vector. Vector we learn that a vector x bar can be, let's say, one-dimensional vector like this. So it's a row vector, or sorry, it's a column vector now. Column vector. Now in this course we will learn that the vector can have an abstract meaning. So this might be a point in the two-dimensional space, but it can mean different things as well. So it can be a polynomial. So for example, let's say that we have a polynomial. So f of t is a node plus a1t plus a2t squared. Okay, we can represent this polynomial by a vector of coefficients. So let's say that we have this vector of polynomial and it's a0, a1 and a2. So this vector in this form represents a polynomial in the polynomial space. We will learn about spaces in this chapter as well. So you might think that this vector is a three-dimensional vector, but in our case it is a polynomial vector. Another example of abstract vectors, that a vector can represent an audio signal. So you can stack up the audio samples in a single vector. And the general form of vector is elements of r or n, r to the power n. So it can be r to the power 10, 20, 100, 1000, whatever you want. Okay. So now we have defined the vectors. We need to define operations on vectors. Operation on vectors, so we have two fundamental operations: addition, vector addition, and scalar multiplication. So those two operations are the main operations that we need to define on vectors. In the future we will learn about more sophisticated, more elaborate operations such as the vector inner product and the norms and so on. Okay, so let's talk about the fundamental role of linear algebra in science and engineering. So actually the first time we encountered linear algebra and matrices and vectors was in systems of linear equations. So let's say that we have a system, a group of linear equations, right? So we have n equations here, and we have here n variables, right? So the way that we solve this system is by putting the coefficients in a matrix A and the unknowns in vector X and the constants in vector B. Now we have this compact form: A times X equals B. So let's take a simple example here. Okay, so yeah, again after more templates. Okay, so let's say that we have those equations. 2x plus, say, x1, 3x2 equals 7, then x1 minus 7x2 equals 9. Okay, so what we do usually is take the coefficients and put them in the matrix. So 2, 3, 1 minus 7. Okay, then we put the unknowns, which are x1 and x2, in a vector, and put the constants in another vector, right? Okay, so we claim that those two forms are equivalent. How so? So let's check them out. So let's multiply them using matrix multiplication. So if you remember, matrix multiplication is you multiply the first term of the row with the first term with the column. So this is number 1. Then you add the second term in the row with the second term with the column, right? If you do this, what you get is 2x1 plus 3x2 equals 7, which is the first for equation. As for second equation, take this, the first element in the second row times the first element in the single column here that we have. So we have 1 times x1 plus minus 7 times x2. So this by this, right, equals the constant. So now we have the same representation. Okay, now this we denote it as matrix A. Note here that the matrices here are denoted by capital letters, and this is denoted by vector x. So when we write it, when the vector is handwritten, we put a bar on top of it, and this is vector b. Okay, so we have a times x equals b. So this is the matrix representation. Okay, in equation 1.2 we have a general system of equations. We have n equations with n variables. Okay, now note this notation: a belongs to r to the power n cross n, which means when you see this means it's the space of matrices. So every point in this space represents a square matrix that has n rows and n columns. Okay, and those two vectors, they belong to the r to the power n, which means that they are vectors of dimension n. Okay, now we will discuss a few operations on matrices, mainly transpose and inverse. But before that, let's say that we have a rectangular matrix A that belongs to r to the power m cross n, and another matrix B which belongs to the same space. You see, sometimes we write it m cross n, or sometimes as m comma n. So those two forms are interchangeable, or they mean the same thing. Okay, so the important thing that they have, both of them, the same dimension. Okay, which is m cross n or m comma n. Okay, we can add them directly. So C, which is the new matrix equals A plus B. So we can have element by element additions. So the first element in A, which is the first element in the first row and first column, is added to the first element in B, which resides in the first row and the first column. Okay, so this is simple. This is the addition. How about matrix multiplication? Matrix multiplication, we cannot multiply any two matrices. We have some conditions. The main condition, or the only condition, is that they must be compatible in sizes, meaning that the columns of the first matrix must be equal to the rows of the second matrix. Just like this. Here you can see we can multiply A by B since they have compatible sizes, and the resulting matrix will get M rows times K columns. Okay, and the way that we multiply matrices is quite simple. We've seen before. Just let us have another example. So let's say that we have two matrices, A equals 1 2 3 4, and B equals, let's say, 5 6 7 8 9 10. Okay, so are they compatible? A is 2 by 2, which is a square matrix. B is 3 by 2. Are they compatible? Can we multiply them? No, right? Because 2 does not equal 3. So let's change this matrix. So we let's say that we have matrix B in this form. Okay, 5 6 7 8 9 10. So this matrix is 2 by 3 and is compatible with matrix A. So let's multiply those two matrices. Okay, A times B equals, so let's put them 1 2 3 4, this 5 6 7 8 9 10. Okay, so let's multiply them. So as we said earlier, right? Okay, before that, what will be the resulting matrix dimension? It will be 2 by 3, right? So it will be a fat rectangular matrix. Okay, so we multiply 1, say here, let's change the color. So 1 by 5 plus 2 by 8. 1 by 5 is 5, 2 by 8 is 16, so we have 21, right? So let me get my calculator just to be sure and not make any mistakes. Okay, now the second element here, we have we multiply 1 by 6 and 2 by 9. So 6 plus 18, 6 plus 18 is 24, right? And again 1 by 7 plus 2 by 10, which is 27. Now let's change the color, go green. 3 times 5 is 15, plus 4 times 8, which is, now we have 55. Now we have 3 times 6 plus 4 times 7. 3 times 6 plus 4 times 7 is 46. Lastly, we have 3 times 7 plus 4 times 10, which is 61. So this is our matrix. Okay, this is our example. as we said earlier, they must be compatible. Hence, we cannot reverse their order. A times B does not equal B times A, of course. So this is the general case. We might find some cases that they do equal each other, but it's not the general case. Okay. Another property that the multiplication is associative, so we can uh, combine them. So we can find, let's say, D equals A times B, then multiply it with C, or say B times C is equal E, and then multiply A times E. So they are associative, they are distributive. We can distribute the multiplication on the summation or subtraction from the right or the left. Okay. Now we introduce an important matrix, which is the identity matrix. Okay, the identity matrix is a special matrix. It's usually rectangular. So let's say here A is a 2 by 2 matrix. So let's say, okay, A here is R close to the power 2 times 2. Then I2 equals what? 1, 0, 0, 1. Okay, multiply I2 with A. So let's use our example here, right? So let's take another. So we have the same matrix A. Let's put it again. 1, 2, 3, 4, and we have I2, which is 1, 0, 0, 1. Multiply I by A. Okay, 1, 0, 0, 1. You can see that we get the same matrix, right? How come? 1 times 1 plus 0 times 3 is 1. 1 times 2 is 2 plus 0 times 4 is 2. Same thing here. 0 times 1 is 0, and they have 1 times 3 is 3, and the same thing here. Okay, so let's say that we want to multiply them from the left. So A times I, is it the same thing? Let's see. It should be the same. 1 times 1 is 1, 2 times 0 is 0, 1 times 0 is 0, 2 times 1 is 2, 3 times 1 is 3, 4 times 0 is 0, so I have 3, and the same thing in the last element. So we have seen that both multiplications from the right and from the left, they are equivalent, which is a good thing. Okay, great. Now let's move on here. Now we have another operation. It's called the transpose. So let's say that we want to find the transpose. The transpose, we denote it by a superscript T, like this. So we want to transpose this matrix. How to do it? Simply we flip the rows and columns. So we have this row becomes a column, and this row becomes a column. So this is the transpose operation. It's very simple. Okay, mathematically you can define by this form, right? You swap the rows and columns, and as you see here, I, J, it becomes J, I. Okay. Now we define another important matrix for square matrices on is called the inverse matrix. So what is the inverse matrix? It's the matrix that we multiply from the left or the right, and we get the identity matrix, and we note it by a superscript -1. And it's a very difficult matrix to find, so we usually like to avoid computing it, but sometimes we must compute it anyways. So we have some nice properties here that the inverse can be distributed upon multiplication, but you have to reverse the order. It cannot be distributed upon or on addition. A nice, very obvious property of the transpose is if you do it twice, you get back to the original matrix. And similar to the inverse, the transpose can be distributed on multiplication, but you have to reverse the order as well. Fortunately, you can distribute the transpose on addition, and you can change the order of transpose and inverse. And usually in some references you can find this notation: minus t means that I'm doing inverse and transpose in the same time, right? Okay, now having said that, we are ready to solve the famous ax equals b equation. How to do it? We multiply both sides from the right by a inverse here and by a inverse here. So we get here a times a inverse equals what? Identity. Identity times x is x, and we left with the right hand side with a inverse times b. Okay, a must be square and invertible, meaning it must be full rank, as we learned in the linear algebra course. Full rank meaning that all the equations are unique, or meaning independent from each other. Okay, they are not scaled copies of each other. Now what if the matrix is not square? How do we solve such system, meaning that we have more equations usually than variables? One way to do it is to make the system square. How? You multiply it by a transpose from the right hand side, and you do the same thing to the left hand side, to the right hand side, b, since it's an equation. Now this is rectangular, it was rectangular matrix, and now it is a square matrix. How come? So we have it's m times n multiplied by n. Sorry, let's do it again. So here it's a transpose, right? So it's n times m multiplied by the original matrix m times n, right? So they are compatible. Now we get n by n. So this is an n by n system, right? And this would be n times m, and this, the b is m times 1, so we get n times 1, right? Now since this is a square matrix, we can find the inverse of it, which is this matrix here, and now we find the solution. This is called pseudo-random of pseudo-inverse form, okay, of the matrix.